All right, guys, so let's look at example number 2 from our notes packet. Okay, this is a 25 kilogram box is sitting at rest. The coefficient of kinetic friction between the ground and the box is 0.55, and the coefficient of kinetic friction is 0.65. Find the force necessary to get the box moving, and then the force necessary to keep the box moving. All right, so the first thing that we're going to do is we're going to find the force necessary to get the box moving. Now, what I would like for you to do is be in the habit of, well, this is a force question. If this is a force question, we should draw a free body diagram. So here's a free body diagram on the box. We've got the box. We've got the force of gravity down. We've got the normal force up. Those two, of course, are equal because it's not accelerating up or down. And then if we are pushing on it, then we got a force of the push this way. And you could call that the normal force of your hands or something like that. That's fine. But force of the push is enough there, recognizing that it is a normal force. And then the reason why it is staying where it is, the reason why it's not moving is because we have friction that is opposing that attempt to move. Now, remember, we have two types of friction. One type of friction is the type of friction when something's at rest that opposes the starting to slide. That's our static friction. So that's what we have first, is we have some static friction. The box is not moving. We push on it. It stays at rest because there's some static friction that is opposing the attempt to slide. All right. Then once it gets moving, we now have the kinetic friction. And that's exactly what we'll look at in part B. All right. Now, you may say, well, I can already write a couple of equations, right? I can do a horizontal equation. Now, remember, for the first situation, it's necessary to get it moving. So we're going to look at how much force can friction give where it stays at rest. Okay, so this first situation is staying at rest. So we would go, we've got the force of the push, which is to the right. And then we've got friction, which is to the left. And this is sum of the forces equals ma. And the acceleration here, of course, is 0 up until the point where we give just enough force that it's more than that amount of static friction. So what we're looking at right now, I'm going to put a little s there to remind me that I'm looking at the static friction because it's at rest. Okay. The second piece here, I could do a equation for the normal forces as well, which would just be the normal force of the ground. Now that's the important one when I'm looking at friction, because the friction is between the box and the ground. So that'll be important later. And then I've got the minus Fg, which that's also equal to 0 because the box isn't accelerating up or down. All right. So we've got our two equations there. Now we recognize that I can get the force of gravity, right? I can always get that if I have the mass, because the force of gravity is just mg. So I can solve for that because I've got the mass up here and I know that g is 9.8 on the surface of the earth. So I could solve for the normal force. Up here, I have a little bit of a problem. The question is, what is the force necessary to get the box moving? So I'm looking for this. So in order to get that, I need to know how much friction there is. If I don't know how much friction there is, then I won't be able to get this. So my first step is I need to find out how much friction there is. Now, how do I get that? Well, you remember our equation from class, which was that the force of friction, in this case, we're looking at the static friction, will be equal to the coefficient of static friction times the normal force. Now, remember this coefficient of static friction and the normal force, this force of friction can change until it gets up to some maximum value. Remember, I was pushing on the table with just a little bit of force and there was a little bit of friction. I pushed a little bit harder, there's a little bit more friction, and I can exert force until I get to some maximum value. So that's what we can calculate when using the coefficient of friction here. All right, so we can go ahead and calculate that. First, I'm going to need, of course, the normal force, which is, it's a good thing I wrote out my equations because I'm going to need that to get the normal force. We recognize that the normal force then is equal to, normal force minus the mass, which was 25 kilograms, times g, which was 9.8 meters per second. That should equal 0. Go ahead, take just a second, see if you can calculate that. When I do it, I get 245 newtons. Okay, so I multiply those, add it to the other side, and I get that the normal force is 245 newtons. Now, I'm not going through the algebra. I believe that you can do the algebra. If you have a problem with that, let me know. I'll help you out with the algebra part of it. So I've got the normal force is 245 newtons. So now I can take that, I'm going to put it into my friction equation here. So I'm going to be finding the static force of friction, which is equal to the coefficient of static friction, which is 0.65, times the normal force, which was 245. And when I multiply 245 times 0.65, I get 159.25, which that's enough to say static force of friction is 159 newtons. Okay, 3 6/8, that's plenty. 3 digits is enough. Now, that's the force of static friction, but that's not what the question was asking. The question was asking how much force is necessary to get it moving. Well, static friction can provide anything up to 159 newtons of force. So if I put that in this equation right here, if I say static friction can go all the way up to 159, then I get that the force of the push is 159 newtons, because I add that to the other side. And so I find out that if that's the maximum, any force more than that, and the box is going to start sliding. Okay, because friction can only give that much force as static friction. Anything up to that, but no more. All right, so that's question A. We found out that the static friction was 159 newtons. Any more force than that, and the box is going to start sliding. Now, once it is sliding, how much force do I need? That's the next question. The force necessary to keep it moving. And so we get to basically go through the same process again, except this time, obviously the normal force isn't going to change, right? That just depends on the weight. So that's not going to change. But what is going to change is that we're going to go in, and instead of the static force of friction, we now want the kinetic force of friction. And so we'll go ahead and find that. We'll say the kinetic force of friction is equal to the kinetic coefficient of friction, again, times the normal force. And we can put those numbers in, and we should be able to then solve for the force of friction there. All right, so let's go ahead and put those numbers in. We'll switch back to black just because it's a little bit easier to see. We'll say the force of kinetic friction is equal to the kinetic coefficient, which right here is 0.55, times the normal force, which we said was 245. And if I do 0.55 times 245, then I get 135. Again, rounding to 3 6/8. So friction is 135 newtons. Again, I can put that into this equation. And once it's moving, how much force do I need to continue that motion? The forces just need to be balanced. So if the force of friction is 135, then the force of the push only needs to be 135. And so once again, that should correlate with our normal experience and understanding, in that the force to get it moving is more than the force required once it is moving. All right. Okay, that's example number 2. Let's go on to number 3.